Hello class, and welcome to section 4.4, which is about linear equalities with two variables. By the end of today's lesson, you will be able to graph the solution for inequalities with two variables. An inequality with two variables is in the form y equals mx plus b, but the equal sign has been replaced with less than, greater than, or less than or equal to. So this is what happens when we have linear equations on the coordinate plane, but we have, instead of an equal sign, one of our inequality values. The solutions are all of the ordered pairs that make the inequality true. It'd be impossible to list out each of those ordered pairs individually, so instead of listing them out, we shade in whichever side of the graph is going to give us all of the correct answers. So we're going to use some shading in our problems in order to actually show the answer. There are two different types of linear inequalities when it comes to two variables. The first one is a closed boundary line inequality, and this is graphed with a solid line, much like you would normally graph a line. And then you are going to shade one of the sides of that line. The points on the line are included within the solution set. So anything that fell on the line would be part of the solution set. Whereas with our open boundary line, that's a dashed line. So we're going to change how we graph and graph it with a dashed line. And that means everything that is on the line is not actually a solution to the problem. So just like when we graphed single inequalities, we had the open circle and the closed circle. When it comes, to two variable inequalities, we have the dashed line, which is the same as the open circle, and the solid line, which is the same as that closed circle. So that's going to be the two ways we can graph our lines. First of all, we are going to test to see if a solution is possible for the inequality. So we're going to plug our points into the equation, and the first thing we would do is this is our x value, the -3, and our y value is the 4. So for this first ordered pair, we'd plug it into the inequality, and we would say 4 is greater than or equal to 3 times -3 plus 8. When I solve that, I get 4 is greater than or equal to -9 plus 8. 4 is greater than or equal to -1. That is a true statement, so yes, this would be a solution. It'd be part of the solution set for this particular inequality when we put it on the graph. Another point that potentially could be part of our solution, it really could be any point. These are just the two that they give us to test. We're going to say that -3 is greater than or equal to 3 times 4 plus 8. That gives us -3 is greater than or equal to 12 plus 8. -3 is greater than or equal to 20, which is not a true statement, so that would not be part of our solution set. So when it's asking if it's a solution or not, you simply need to plug in and see if it gives you a true statement or a false statement. True, yes, it works. False, no, it does not. Go ahead and try this one on your own. When we plug in, we find that yes, this does give us a true answer to our inequality. So this is just showing things that could work as solutions. Now, when we get to the actual graphing piece, the graphing principles that we learned in Chapter 2 when we were talking about linear equations are the same principles that we're going to use when we are graphing linear inequalities. So this b value is still our starting point. So I'm going to go down on the y. Our y-intercept is -1. My slope is still in front of x. In this case, it's going to be 1 over 1. So I go up 1 and over 1. Now, what changes with the linear inequalities is the type of lines that we are graphing. So because we have a less than sign as part of our equation, our line that we graph is going to be a dashed line. So that means every point that is on this line is not part of the solution set for my graph. And I need to go ahead and drag this momentarily into where it is actually supposed to be. I apologize for that. So we have our linear equation that we have graphed. with a dashed line because we have a less than sign. So now what we need to do with the inequality is figure out which part of this line we are going to shade. One of the easiest way to do this is to test the point 0, 0. So what we were doing before is seeing, is it a solution? You could pick any point on this graph. Generally, I suggest you use 0, 0 because those are going to be your simplest numbers. So I'm going to say 0 is less than 0 minus 1, which is going to give me the statement as 0 is less than negative 1. That is not part of our solution set. That is not a true statement. So everything that does not include 0 is going to be part of a solution set. So for example, if I picked out the point 2, negative 1, if I put in negative 1 for y and 2 for x, I'm going to get an answer that's true. So every point on this side of the line gives you a true statement. That is our solution for the graph. So if you plug something in and it doesn't work, you go to the opposite side of the line. If you plug something in and it does work, you stay on that side of the line. Another way to think about it is if your variable is on the left side and your symbol is less than or equal to, you're going to be below the line. If your y is on the right, or again the left side, and it is greater than or equal to, you're going to be shading above where that line is. But that only works if your y is on the left side. So I'm going to go through another example here. This one, our y-intercept value is at positive 4. My slope gives me up 2 and over 3. In this case, I've got a greater than or equal to, so I'm going to graph with a solid line. Because of that equal to part, that means that my answers are included in the boundary line, so that's what the solid line means. It's like having our closed circle when we graphed single variable inequalities. So we've got our line with a solid line because we have the equal to part. We put our arrows on the end. Now we need to test a point. Again, I'm going to choose 0, 0. So I'm going to say 0 is greater than negative 2/3 times 0 plus 4. Negative 2/3 times 0 is 0, plus 4 is 0. So 0 is greater than or equal to 4. That is not true, so we cannot shade the side below. So we are shading above that line. Again, like I said on the last slide, if y is on the left and we've got greater than, we shaded above where that boundary line was drawn. Go ahead and try this one on your own. We start at 5, we go up 1 and over 1. It is a solid line because we have equal to. 0 did not give me a true statement, so I'm going above that line. Just like when we have regular linear equations, sometimes we have to isolate y in order to graph our linear inequalities. So I'm going to start this one by saying subtracting 6 from both sides. So I've got negative 2y is less than or equal to negative 6 plus 4. Then I'm going to go ahead and get rid of that negative 2 by dividing negative 2 on all 3 pieces. Remember, if you multiply or divide by a negative, that inequality sign flips. So that's something we need to remember from chapter 1. If we multiply or divide by a negative and we've got an inequality sign, we flip the inequality sign. So the line that I am now graphing is y is greater than or equal to 3x minus 2. So I'm going to start at negative 2, go up 3, and over 1. I'm going to be using a solid line because I've got that less than or equal to part. So I'm going to go on my graph and draw that in, making sure I add arrows on both ends to extend that line all the way out forever and ever. When you test your point, you plug it back into the original equation. Just in case you made some error while you're solving and you graphed the wrong line, you still want to make sure you get the right solution set for the problem. So you always plug back into the original equation. So again, I'm going to use 0, 0. So I've got 6 times 0 minus 2 times 0 is less than or equal to 4. So I've got 0 minus 0, which is 0, is less than or equal to 4. That is a true statement. So I am going to go on the side with 0, which in this case is to this left portion. So again, we rearranged, got y by itself, plugged 0, 0 into the original equation, and that's what gave us our final solution. Go ahead and try this one on your own. Solving for y, it is a dashed line this time because we just have the greater than part. And then we plug in 0, 0, that answer doesn't work. So we're shading on the opposite side of that line, or above that line. Sometimes you are only going to have one variable. Just like when you have one variable in linear equations, this is either going to be a vertical or horizontal line. So when I solve this one by dividing by 4 on both sides, I end up with y is greater than or equal to 5. So when I put that line on there, I've got a solid line because I've got that greater than or equal to part, and I'm up at 1, 2, 3, 4. Y is equal to 5. And then when I put in that solid line, it is a straight horizontal line because we want all of the places where the y value is equal to 5. Again, plug into that original equation. 4 times 0 is greater than or equal to 20. 0 is not greater than or equal to 20. So we are shading above that line, away from the point 0, 0, because it's not part of my solution. Go ahead and try this one on your own. When we solve, this is now an x, so that gives me that vertical line. 0 is part of the solution set, so we shaded to the left of that line. Last thing we're going to go through, quick word problem here. The Science Club sells t-shirts for $10 and keychains for $2. They want to make at least $500. Write and graph the inequality. It does not specify which one is x and which one is y here, so you can always assume that the first one is going to be x. So I'm going to say I've got 10x plus 2y is at least, so we want to be bigger than or equal to $500. Now I need to solve to get y by itself, so I'm going to subtract 10x from both sides, giving me 2y is greater than or equal to negative 10x plus 500. And then I'm going to divide everything by 2. So I've got y is greater than or equal to negative 5x plus 250. So I'm going to go ahead, and I need to be careful what I'm counting by now because I'm starting at 250, but I am going down by 5. So now I need to figure out how I'm going to scale this graph. 250 is my y-intercepts, but I'm counting down by 5s. So I'm going to have to find a way to reconcile those two things because those are pretty big number differences. So I'm going to want to make sure I can include 500. So I'm going to go ahead and count up by 50s. And that's going to give me the following graph once I plug all of those values in. And then when I'm going across, I need to be going down by 5 and over by 1. But if I'm counting by 50s here, I'm probably going to want to count by something bigger on my scale going on my x as well. So I'm going to count by 10s because what that will mean for my slope now is that instead of being 5 over negative 5 over 1, I can think of it as negative 50 over 10. So negative 5 over 1 and negative 50 over 10 are the same numerical amounts. It's just a different version of the fraction. So when I graph, I'm able to start at positive 250, and then I can go down 50 and over 10. So I'm able to scale the graph so that even though I have that -5, I can still get my graph to work. What I need to do then is I've got my solid line, and I'm going to put my graph in right here, and I am going to stop at that x-axis. The reason I am not continuing to extend that line is because that would mean I am going below 0, which we can't have negative money, we can't have negative t-shirts, and we can't have negative keychains. So all of those possibilities would be below that x-axis, so I don't want to include that area. Now I still need to finish graphing by deciding if a point works or not. So I'm going to plug in 0, 0, because that is part of that's part of something that could be included. So I'm going to say 10 times 0 plus 2 times 0 is greater than or equal to 500. 0 is greater than or equal to 500 is not a true statement. So that means that everything above, all of these points above the line, are something that could work. Now you need to determine if they sell 30 t-shirts and 90 keychains, will they make enough money? The answer is no. This is not a possible solution. If you look back at our graph, 30 and 90 is going to be below that line, so it wouldn't fit in the area that is shaded. So you either could have gone through and proved it numerically, or use your graph as justification to say that that's not part of the solution set. If you have questions about this or anything else from the lesson, please let me know when you get to class.